In this lesson, we will discuss partitioning-based clustering, specifically the k-means method. We will start with basic concepts of partitioning-based clustering, go over the k-means clustering method, followed by discussions on its efficiency and challenges, and finally, we will list a few variations of the k-means method. What is the idea behind a partitioning method? Essentially, it tries to discover groupings in the data by optimizing a specific objective function and then iteratively improve the quality of these partitions. In a k-partitioning method, we are given a dataset of n objects, and we want to divide it into k clusters. So the goal is to optimize some objective function. For example, we may want to minimize the total distance between each data point and its cluster center. A typical objective function in k-means is the sum of squared errors, or SSE. Here, ck is the centroid for the cluster, and xi represents each data point that belongs to that cluster. In other words, we are trying to find a partition of the dataset such that the sum of squared distances between each point and its cluster center is as small as possible. Now, the challenge is that we don't know the cluster centers ck in advance, and we also don't know the partitionings, which makes this as a difficult problem. Since we don't know the cluster assignments, we have to find the clusters and their representatives at the same time. Now, in theory, we could try every possible way to partition the data and find a global optimum, but that would require checking a large number of possibilities, which is computationally infeasible. Instead, we use a greedy algorithm such as the k-means or k-medians, k-medoid. These methods still don't guarantee the absolute global optimum, but they work efficiently and usually produce good clustering results in practice. The basic idea in k-means is that each cluster is represented by its center. We often call that center a centroid. Given k, the number of clusters, k-means works as follows. First, it selects k points as initial centroids. Typically, the points are generated randomly within a data range. Then, the algorithm enters the iterative process, form k clusters by assigning each data point to its nearest centroid, which means every data point computes its distance to each of the k centroids and picks the closest partition as a group. Next, the algorithm recomputes the centroid of each cluster by taking the mean of all the points assigned to that cluster. This step updates the position of each centroid based on its new members. The algorithm repeats these steps until a convergence happens, which means the cluster assignments stop changing or the centroids stabilize. In most cases, we use the squared Euclidean distance as a similarity measure, but other measures such as the Manhattan distance, L1 norm, or cosine similarity can also be used. Here is a visualization. We start with the original dataset presented with the black points. Now the algorithm randomly selects the initial centroids. K equals to 2, so we have two centroids, the red star and the blue star. They are placed randomly at first. Next, Each data point looks at both centroids and computes its distance to each one. Whichever centroid is closer, that is the cluster that it's going to join. So if a point is closer to the red star, it joins the red cluster. If it's closer to the blue star, it joins the blue cluster. Once all points have been assigned, the algorithm recomputes the centroids. That means we take the mean of all of the data points in each cluster. So the red cluster finds its average location, and that becomes the new red star. The blue cluster does the same thing to find the blue star. Now that the centroids have moved, the points have to check again, recompute the distances, and change a clustering if needed. The process will continue until a convergence happens. This is basically the k-means algorithm, simple to implement, works reasonably well in many cases. One more comment about the convergence criterion here. Some implementations like to limit the number of iterations. So in addition to the stability of the cluster, additional condition can be added to limit the number of iterations. Now let's take a look at some of the practical points about the k-means method. The runtime complexity of k-means is big O TKN, where n is the number of objects, k number of clusters, t the number of iterations. Usually both k and t are much smaller than n, so overall this is a reasonably efficient algorithm. One thing to keep in mind is that k-means often terminates in a local optimum. So depending on how the algorithm initializes the centroids, one might end up with different final clusters. That's why initialization is really important to find high quality clusters. Another thing, the algorithm needs to specify k, the number of clusters in advance. Typically, as one increases the value of k, the sum of squared distances within the cluster keeps on decreasing, but this will level off after a certain point. So usually look for that point of slowdown, sometimes called the elbow method. In practice, people just run k-means for a range, k values, and then choose whichever one works best given a criteria. K-means is also sensitive to noisy data and outliers because the algorithm computes the mean of the points. It only takes one extreme data point to pull the centroid away. To handle that, there are more robust versions like the k-medians or k-medoids, where the cluster center is based on medians instead of means. Another limitation is that k-means works only for continuous numerical data. That's because it relies on computing distances like Euclidean distance or Manhattan distance. For categorical data, there are extensions such as the k-modes that adapts the idea but using the modes instead of the means. Finally, k-means is not suitable for discovering non-convex shapes because it tends to find spherical cluster because it's a distance-based centroids. For complex or irregular shapes cluster, we often use approaches like density-based clustering or kernel k-means. Finally, there has been a lot of work on improving the initialization and performance of k-means. The first line of improvements come from choosing better initial centroids, because as we have seen, random initialization can sometimes lead to poor clustering results. There are several clever algorithms such as k-means++, intelligent k-means, and even evolutionary approaches like genetic k-means. Then there are methods that choose different representative for clusters, for example, k-midoids, k-medians, and k-modes. These help handling the cases where the data are categorical or when we need more robustness against outliers. Finally, there are more general versions that apply feature transformation techniques like weighted k-means and kernel k-means. And these methods can discover clusters that are not necessarily spherical or convex in shape. In summary, we discussed partitioning-based clustering, specifically the k-means method.